So we'll talk a little bit about um, stability of colloidal dispersions. Okay. So what do you understand if I say that the colloidal dispersions are stable? Any thoughts? Some thoughts? So we can think about stability as two different in two different ways, right? I can, as I mentioned already, I can think about something called as a uh, stability against sedimentation, right? That means I have the same dispersion. If I leave it for a while, everything goes here, right? They all settle down. But typically, I said that such a thing will only happen if you're working with what are called as colloidal or suspensions, right? Not okay. Typically, this will happen when you're working with suspensions where the particles are larger in size, and because you work with very small particles, it is assumed that the gravity doesn't play a role. Okay. However, what could happen is this, right? What you're looking at is two pictures. Picture A, where you have a stable colloidal dispersion. I have really not defined what is stability, but I'm saying that it is stable because all the particles are in their individual state. Okay, they are happy being in the fluid. Okay, however, we know that the because the particles are very small in size, they have a high surface area, right, which makes them prone to what is called as aggregation. Okay, again people use term called aggregation, coagulation, okay, and things like that. Okay, so what you have here is an example where you have formed what is called as an aggregate which contains multiple particles. Okay, so why do you think things will go from this state to this state, or can you think about ways by which things can go from this to this state?
Interaction between particle particle is more favorable than the particles and the continuous phase
Okay, so the answer that I get is that if the interaction between the two particles, okay, is more favorable than the interaction between the particle and the fluid. Okay, yeah, so we can think about along those lines. Now, okay, we'll again spend a little bit of time talking about interactions in the next few lectures. Um, so what will happen is this, right? So if you have particles in a fluid, um, you know that these particles are not stationary, right? They are being continuously hit by the solvent molecules in which the particles are dispersed. That means for every particle there are a lot of solvent molecules which are hitting. Okay, they are hitting everywhere. Okay, because of which the particles can move around. Okay, so whenever you take a dispersion, okay, and if you say that I have this dispersion at a temperature T, okay, so the energy that the particles have, okay, it is given by what is called as kBT, or the thermal energy. Okay, this kb is what is called as a Boltzmann constant, okay, which has a value of 1.38 into 10 power minus 23 joules per Kelvin. Okay, that multiplied by the temperature will give you a unit joules, which is a unit of energy, right? Therefore, the moment you have any fluid or a colloidal dispersion at some temperature T, invariably all the molecules as well as the particles in the fluid have this thermal energy kBT. Okay. Now you can ask a question as to what, now I am drawing these particles very far apart, right? They are sufficiently far apart. What can bring the particles close to each other is this thermal energy, right? There are thermal fluctuations, they are moving around. Okay, when they are moving around, they could approach another particle. Okay, when they approach another particle, the particles may either attract or repel. Okay, that depends on the type of the particle that you are trying to deal with. Okay. Now here is an example, okay, where, so what you have is some energy, in this case it's called as its interaction energy, okay, or also called as a free energy, okay, that's this. And you will see in colloids literature that whenever people talk about interaction energy, you always scale with kBT, okay. The reason is this, right? When you do interaction energy calculations, I said that the Boltzmann constant is 10 power minus 23, right? Now if I multiply that by, like say if the temperature is 300, right, this energy will be of the order of 10 power minus 21, right? So when you do calculations, when you get numbers which are 10 power minus 21 joules, so you may say that, look, it's too low, it's not important, okay. So just to get a feel for the numbers that you get out of such calculations, you typically always scale the interaction energy with thermal energy, so that I can compare and say, hey, the interaction energy that we are obtaining, it's 1 times kBT, 2 times kBT, 10 times kBT, something like that, okay. Therefore you'll always see that people who do interaction energy calculation, they always scale the interaction energy with the thermal energy. So what is plotted here is this interaction energy, okay, as a function of separation distance, that is plotted on the x-axis, okay. So the way to think about this interaction energy is, it is the energy with which the particles attract or repel given whatever distance they are at, okay. So if you look at this, let's trace this plot, okay, that's your x-axis, okay. So the interaction energy goes something like that, right. So people typically talk about this minima that you have is what is called as a primary minima, okay, or also called as a global minima, okay. This is what is called as a secondary minima, okay. Now what you have here is a barrier, okay. So in order for the particles to approach and reach this primary minima or the global minima, they have to cross this energy barrier, okay. Now if the energy barrier that you have, okay, if it is of the order of kBT, okay, because the particles already have a thermal energy, and that thermal energy in fact is kBT. If the energy barrier is also of the order of kBT, what can happen is these particles can easily cross the energy barrier, and then they can come and reach this global minima state, where the particles can form aggregates like this, okay. Now once the particles form such aggregates which are essentially at a very small separation distance, right, this is delta is a separation distance, okay, that corresponds to this global minima, okay. So once they reach that place, they are aggregated, it's very difficult to separate them out, okay. You can do sonication, of course it depends on this again, it depends on what is this, the minima is, right, what is the location of the minima. If the location of the minima is really large, that means it is practically impossible to separate these particles once they aggregate. However, if this this minima is of the order of maybe few times kBT, then sonication or anything may be able to rip them apart, okay. So therefore So if you have cases where the energy scale associated with this barrier is of the order of thermal energy, such dispersions are said to be what is called as kinetically unstable, because the kinetic energy that the particle possesses because of the thermal energy, it is good enough to overcome the barrier and then make it go from this state to this state. Okay, such a process or such a case is referred to as a case where you have dispersions which are kinetically unstable. Okay. On the other hand, you could have a case where the energy, okay, which corresponds to this barrier, it could be much larger than kBt. Okay, when I say much larger than kBt, it could be 100 times kBt, or several orders of magnitude larger than kBt. Okay, such dispersions are said to be kinetically stable. Okay, that means there's an energy barrier associated with the particles being in a dispersed state and a destabilized state. Okay, if the height of this energy barrier is of the order of kBt, then the dispersions are kinetically unstable. If the height of this energy barrier is much larger than kBt, then such dispersions are kinetically stable. Okay. Yeah. So any questions with this? Okay. So now one can ask. Yeah, you have a question. Yes. Yeah. So for stable colloids also, everything depends on this everything depends on this energy, right? So if I have a stable dispersion, okay, I could have, so again, stability is a very relative term, right? When I say stable, I could have a dispersion of particles, okay, homogeneous dispersion, it may be stable for a day, but if you wait for a few days, things may, coagulate. Okay, so everything depends on, so what will happen is this, right? So the particles are moving around because of Brownian motion, they approach each other. Now if the okay, let me put it this way. So what you can do is, I can play with this energy barrier, right? I can play with this energy barrier. Now say that I have a dispersion where this energy barrier is like, say, 1.5 kBt. Okay, now you could ask a question as to, look, something where the energy barrier is 1.5 kBt, is it highly stable? No, right? Because so of course if you look at 1 times kBt and 1 times 1.5 times, they are comparable. Okay, of course if I talk about 1 kBt and 100 kBt, they are 2 orders of magnitude larger. Therefore definitely such colloids will exhibit a better stability. Okay, so I'll come back and answer your question. Before that, I want to talk a little bit about something called as thermodynamic stability. Okay, so these are dispersions which exhibit what is called as ultra long stability, because such colloidal dispersions are formed because of what is called as a thermodynamically favored reduction in the free energy of their formation. Okay, I talked about the formation of micelles, right? So when you start with fluid and start adding surfactants, I said that they form micelles, right? The formation of micelle is a process where there's a overall reduction in the free energy of the entire system. Therefore, okay, such association colloids in water, they do exhibit ultra long stability. That means I take a dispersion of micelles, keep it for years and years. If things don't change, if the temperature doesn't change, if the solution conditions don't change, they continue to exist as micelles. Okay, Another example is what is called as a microemulsions, okay, which are typically formed when you have oil, water, and a surfactant. What you're looking at is some example from our lab. This is a pure diesel, a fuel that people use, right? And then this is a diesel microemulsion. This has diesel plus water plus a surfactant called AOT. Okay, you can look at if you look macroscopically, you don't see anything, right? It's very difficult to say that, look, I have water in there. Okay, it has some amount of water and some surfactant, but it looks very transparent. Okay, that is because it contains very tiny reverse micelles. Okay, so the micelles are something like that I said, right? Reverse micelle will have water inside and an oil outside, and the surfactant molecules are arranged something like this. Now, if I look at the size of the dispersed phase, okay, that is these micelles, reverse micelles in water, in oil, you look at the size, right? This is measured as a function of time, 180 days, that's 6 months. Okay, practically there's almost no change. Okay, however, if you take a dispersion of kinetically stable colloids, okay, you could also have a case where, see, there are kinetically stable colloids which are available in the market, which do exhibit a shelf life of years if you want. Okay, but however, I can't say that such colloids are infinitely stable or that they are stable forever. Okay, it's because at some point the thermal energy is going to overtake and they're going to aggregate. So these are the two examples of what are called as thermodynamically stable colloids. The other examples of thermodynamically stable colloids are solutions of polymers. Okay, I can take water, put a little bit of polymer like PVA, polyvinyl alcohol, make a solution, keep it for this tip, you don't see any changes to their size or aggregates, no aggregation, right? So final example of a thermodynamically stable state one could achieve is cases where you work with charge stabilized colloids. Now, I said that when I say charge stabilized colloids, you should imagine that I have a dispersion, say the continuous phase is water and your dispersed phase is particles, and the particles have some charge. Okay, that is a charge stabilized dispersion. Okay, in such a case, what you will have is there is a high energy barrier for them to aggregate, and they are actually an example of kinetically stable colloids because they have an energy barrier much larger than kBT for their aggregation. Okay. However, when you have a large collection of such particles in the fluid, what will happen is they exhibit a crystal state. Okay, I was showing you some images the other day, right? So these particles, they form what is called a crystalline state, where they are closely packed, periodic arrangement. Okay, and such crystals again are an example of thermodynamically stable states because again their formation leads to reduction in their free energy. Okay, so that's something about the stability. So maybe I'll stop here, and then we will look a little bit about some properties of colloid dispersions in the next class. Okay.